Okay, folks, it's time to begin. So it looks like the plan for today is to continue our discussion of the Zeeman effect. And then the new thing for today will be to discuss the last perturbation for hydrogen, which is hyperfine coupling. That's the plan. All right, so let's see. So last time, let's sort of remind ourselves what was happening last time. We had introduced the Zeeman effect. And the Zeeman effect was basically you have a magnetic field which comes from a solenoid. You just have a battery and a solenoid and it creates a magnetic field. And here's the hydrogen in a glass tube. And then you look to see what the energy levels are difference in the hydrogen. And so we saw that the Hamiltonian for the Zeeman effect, which comes from just negative mu of the electron dot B, is equal to EB over 2m times LZ plus 2SZ, which we can also write if we want. Sometimes it's convenient to write this as JZ plus SZ. It's the same thing. And then we saw that there were then 3 regimes. The simplest regime is the first one, the strong regime, which occurs when the Zeeman Hamiltonian is way bigger than the fine structure. And then what happens is we see that the Zeeman effect splits all the M sub L and M sub S levels, meaning that they're given different energies, they're split. And then we talked about the weak field, which was the next easy one, weak, in which case the Zeeman Hamiltonian is way smaller than the fine structure. And in this case, we see that the Zeeman effect splits the M sub J levels and also different L levels within the degenerate manifold. But now we're going to do the third regime, which we had not done before. And this is the hardest one, is the intermediate field regime. And in the intermediate field regime, the Zeeman splitting is on the same order as the fine structure. So now we cannot push one or the other off into the perturbation. Now they both are in the perturbation. And so we see now that we have the Hamiltonian of the system is equal to H naught, which is our normal hydrogen, just the kinetic energy plus Coulomb. But now we have the perturbation, but now the perturbation is equal to the Zeeman effect plus the fine structure. And so that's what makes it so hard, is that we have to put both of those terms into the perturbation. And it makes it much harder, where the Zeeman effect is going to give us the, that's going to give us, say, the JZ plus SZ perturbation, and the fine structure is going to give us the P to the 4th perturbation, the relativistic perturbation, plus the L dot S perturbation. So those are all in there. So we see now that the perturbation is much more complicated. We have the EB over 2m. That didn't work. JZ plus SZ plus the F of R L dot S times L dot S plus, and now the relativistic term is minus P to the 4 over 8 M cubed C squared. Okay, so that's what we have to deal with. And so now we want to find, the question is always, what is the change in the energy levels due to the Zeeman effect? So now we ask that same question that we asked before. What are the change in energies due to the Zeeman effect? But now we're in this new regime, this intermediate field regime, where now the perturbation is different than it was before. So the question is, what do we do? And the answer is always, the first thing we always try is perturbation theory. Let's do perturbation theory, just like usual. But now we have to ask the same usual questions. The first question is, which basis will we try? Basis. To do perturbation theory, the first thing you do is you pick a basis. And so to pick the basis, we only really have two choices of bases that we like. One basis is the psi n l m sub l m sub s basis, right? Where that denotes the eigenvalue of the operator L squared. This denotes the eigenvalue of the operator LZ, and m sub s corresponds to the operator SC. And how about this basis? Can we pick this basis? Will this basis work? Somebody answer the question. Will it? For perturbation theory?
No.
Why not?
Well, because one of the terms it won't commute with, like one of the Hamiltonian terms it won't commute with.
Which one?
Can't remember which one. I think it was the weak. No, the strong.
Well, the perturbation is up here. So that's the perturbation, I'm circling it. And so these are the operators that index the different states. So what we got to do to see if it's a good basis, you got to see if this commutes with that, right?
Yeah.
And so what doesn't commute? Can anybody tell me? We did it before. This is the same thing that we did for the this is what we did for the did we do this is what we did for the spin orbit coupling. I'm sorry. Can anybody tell me what doesn't commute?
I think it was the L sub Z and S sub Z didn't commute.
No, they actually do commute, because L sub Z and S sub Z, L is orbital, S is spin, and spin and orbital always commute. So try another one. I will give you a hint. You were onto something, because L sub Z does not commute with something inside of that perturbation. Which one does it not commute with?
L dot S.
That's right. Exactly. We see that L sub Z and L dot S don't commute. And you knew that from our discussion of spin orbit. See, because now the spin orbit is back inside of that perturbation. And also you should remember it now, at least when someone reminds you, that S sub Z also does not commute with the L dot S. And so that means, so we already know that this is a lousy basis. So this is a bad basis. The bad basis, send it to the cornfield. Okay, and so we have to ask ourselves, what's a good basis? So what basis should we try now? Somebody suggest a basis.
The new basis.
What's it called?
It's the NL M sub J M sub J.
Exactly. Some people refer to it as the J basis, but it's the total angular momentum basis. That's exactly right. So let's try that one. Let's try the J basis. And so this one is indexed by the quantum numbers N, L, J, M sub J, which are denoted by the operators L squared, J squared, J sub Z. Now, this is, I think, sort of a subtle point, because this is the basis that did work for the weak field case. And remember, for the weak field case, the degeneracy was in the L and the M sub J, which are denoted, of course, by L sub Z and J sub Z. And so for the weak field case, this is what we did last time. We said that this was a good basis for weak field because it commuted, because the Zeeman term commuted with L sub Z, and the Zeeman term commutes with J sub Z. And we know that the spin orbit commutes with these as well, and because we know that the spin orbit is also okay. And we already know that J basis is good for spin orbit. So the J basis was really good for the weak field. But now there's a difference. There's a difference because of now that we're in the intermediate field, it's different from the weak field. And so we have to ask the question, is it good? Is this a good basis? And it looks, the situation looks almost identical to the weak field case, but there's one crucial difference, and it's not totally trivial to spot it, but it is there. Can somebody tell me what the difference is? What is the additional question that we must ask ourselves now in the intermediate field case that we did not have to ask before?
We know it's commute with the L dot S term, but we don't know about the relativistic term.
No, we did the relativistic term a while ago, and so we know that the relativistic term is okay. So, you know, because we know that the J basis is good for the relativistic term because the J basis gave us fine structure. So we're okay with the relativistic. That was okay. But there's one commutator that we have to check that we did not have to check before. And here I'll put the perturbation here. And there's one operator here that we did not check. Can somebody guess what that operator is? This is an operator, yeah?
Was it the Zeeman operator?
Well, no, the Zeeman is living inside of the H prime.
Is it f of r?
No, the f of r is okay. It's something else.
J sub S.
Say it again, what?
The J sub S operator.
I'm sorry, I don't know what do you mean J sub S?
Never mind.
Okay, you meant, okay, like the J sub Z, maybe, you know, we have the J squared and the J sub Z.
Yeah.
And okay, here's the, okay, let me show the tricky point now. It's a tricky point. Now, if you keep guessing operators, eventually you're gonna get it. There's only, you know, 5 operators, so just go down them. What? Yeah.
Sorry, I do have a question for that part. So for the weak field, when you write down the weak field is degenerate in L and MJ, well, should the operator for L be L squared rather than LZ?
The operator for L is always L squared.
But like, yeah, but when you write it down, you said it is LZ in the weak field, like on the right side of your.
Oh yeah, you're right. I made a mistake here. Thank you for pointing that out. Okay, let's take a look at this. So this is the weak field case. When we looked at the H naught, the unperturbed basis for the weak field case, remember we had our level, you know, our nth level, which is degenerate by 2n squared. So we got a huge degeneracy, but in the weak field case, that degeneracy was already split by the fine structure. J1, J2, J3, J4. It was already split. But now we're in the intermediate. And in the intermediate case, when I look at the nth level, the one we're talking about, it has huge degeneracy, but it's not split. And so that meant that before, for the weak field case, the degeneracy was in the, remember I have the psi NL J MJ, and the degeneracy was in the L and the MJ. But what I'm asking a question now. What, for the weak field case, was there degeneracy in the J state? The J. Was there degeneracy in the J? Yes or no?
No.
That's right. And so when we did our little trick to find a good basis, did we have to check the H prime J squared? Because the J corresponds to the operator J squared. Did we have to check this? Yes or no? Did we have to?
No, we only had to check L and MJ, right? L
Yes.
squared and JC.
That's right, because you only check the operators that denote, that index the degenerate subspace. And J was not, the states are not degenerate in J. So we didn't need to worry about it. But now, so I'll just say here, didn't care. But now I will ask you the question, we are still using the basis psi N, L, J, MJ, but now are our states degenerate in J? Do we have degenerate in J now for the intermediate case? Yes or no? Say it.
Yes.
That's right. So now we are degenerate in J, degenerate in J. And so that means that we now have to check whether H prime commutes with J squared. Because because J squared denotes the index is the degenerate subspace.
Can I ask a question?
Yeah.
like, I don't see why we know that we're degenerate in J in the intermediate case. Like, how can we know that other than like you just
I'll
told
tell
us?
you. I'll tell you. The way that we know it is because H naught is equal to kinetic energy plus Coulomb. And so there's no spin term here. There's no spin term. And so we can rearrange all the spins and it doesn't change the energy.
Hmm. Oh, gotcha.
Okay.
Yeah.
All right. And so, and that's the trick. This is a subtle point. I find this very subtle. And so now we have to ask ourselves whether it equals 0 or not. And so now what we have to do is we have to stick the whole H prime in there. And the H prime is EB over 2M JZ plus SZ plus, I'm just going to say L dot S, okay? I'm going to skip a bunch of writing and then see if it commutes with JZ. And the thing is that what we're going to find is that JZ does not commute with SZ. So, and you guys can find that out on your own. You know, you guys can see that SZ and J squared, if you go screw around with it, does not equal 0, and therefore psi n l j m sub j is a bad basis. Bad basis. Okay. And so that means that you're screwed. You're screwed because you only know two bases. Your NLM sub LM sub S basis and your J basis, and neither of them works in the intermediate case. And so then what you have to do, well, I'll ask you, what do you have to do? You have this degenerate state. You know that the nth level is highly degenerate. It has a 2n squared degeneracy. So there's all these different states in the nth level. I'll write it like this. Now we can keep whatever basis we want. Let's just write it down in the J basis. So n sub L J M sub J. It's a bad basis, but we can write out all the states in this basis. There's 2n squared of them. And we have this perturbation. H prime is equal to the Zeeman plus the fine structure. What do we do? How do we find the delta E? What do we do?
Professor, could I ask a question about the picture that you drawn above?
Yeah.
I guess I just got confused. I understand that like we have a certain amount of degeneracy, but how do we know that there won't be any splitting of the degeneracy? Like in the picture we drew with the weak field and the intermediate field, like that. I guess if you scrolled up a little bit.
The way that we know it is because H naught is kinetic energy plus Coulomb. And so we already know that the n squared level is completely degenerate. We already know it's completely degenerate. All the state, there is no splitting. And so if we go into the J basis, all we're doing is we're just rearranging degenerate states. We're just writing new states as superpositions of already known degenerate states. And the superposition of any degenerate state is equal to a degenerate state.
Okay, thank you.
Okay. So, all right, so we have all these degenerate states and we have this perturbation. What do we do? And there's 2n squared of them. What do we do? Somebody tell me. We did it before once. Well,
diagonalize in the degenerate subspace?
That's exactly right. We have to diagonalize H prime in the degenerate subspace. And that's a big pain in the ass. First, I'll ask, what's the dimension of the degenerate subspace? The dimensionality equals what? Somebody tell me.
Two n squared by 2n squared.
That's right. Well, I would say it's a 2n squared dimension, but then if I construct the H prime matrix, then the H prime matrix will have the size of that matrix is what you just said. So that's what you meant, right? 2n squared by 2n squared. That's right. Because for D dimension, then the matrix, the operators in D dimensions is D by D. Okay, so then we have to construct. So then we must construct that matrix. Construct H prime. And then we have to diagonalize it. So I'm not going to do all that, but I just want to remind you how you do it, because it's actually very straightforward how to do it. It's just very tedious, but straightforward. So I want to just remind you how you do it. So we look at our basis, psi n, l, j, m, j. It doesn't matter which one we pick because it's a bad basis. You know, it's okay to diagonalize a matrix in a bad basis. And so let's write them all out. So there's, all the different states, all 2n squared of them. We're right, just list them. And then what you do is give them a name. We'll call this one state 1, 2, 3. And it's really actually quite arbitrary. You just have to be consistent with your notation. 4, 5, etc. Just give them all a name, index them, and then you just construct by hand. You just calculate all the various matrix elements. H, I, J is equal to state I on the left, H prime, and state J on the right, where I and J span that index. And so you construct them all, and then you have the matrix. H prime is equal to this matrix, H11, H12, blah, 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 N1, blah, 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 HNN, and then diagonalize it. And then the eigenenergies, the eigenvalues are the new energies. Okay, and so that's what you do. So let's not do it, and I think you might have some of this on the homework, but let's just stop there for this. And so that's why that's the hardest one. Okay, so now let's move on to the new topic, which is hyperfine. It's so fine. It's hyperfine. And so the thing about hyperfine is it's a new perturbation. It's the last one we'll talk about. There are actually other perturbations that we won't talk about, but it's the last big important one that we will talk about. Last perturbation for hydrogen. And it's important. It comes up a lot, hyperfine. And so let's discuss it. And so here's the idea. So basically, when we're talking about the corrections to the hydrogen energy levels, they come from the fact that we forgot something. Last semester, when you learned hydrogen, you forgot something. And so far we've been talking about all the stuff you forgot. You forgot relativity. You forgot spin-orbit coupling. You forgot to deal with Zeeman effect. And also you forgot about E-field too, Stark effect, and that's in your homework. But then there's one other effect that you forgot about, and that's hyperfine. And the hyperfine comes from the fact that you have, let's say, the proton of the proton, which is at the nucleus of a hydrogen atom, has spin, S sub p. And that means that the electron is orbiting it, and that has spin, S sub e. And so what is the interaction? that we forgot? Can anyone tell me? And don't just say hyperfine. Tell me in more detail. What is it? What is the interaction that we forgot? What is the energy that's, you know, what's causing some new energy? And remember that we always start with classical, okay? Start with classical physics. So the coupling is classical. Start with classical physics. So somebody tell me, what classical interaction did we skip?
Dipole-dipole interaction.
Yeah, that's right. That's exactly right. Dipole-dipole interaction. That's exactly right. Dipole-dipole interaction. And that comes from the fact that the spin, the proton creates a magnetic field, because we know that if you have a spin, then we know that for any charged particle, any charged particle with spin has a magnetic moment. Mu for that particle is equal to G, the gyromagnetic ratio, times the charge, divided by 2m times the spin of that particle. That's the rule for particles with spin. The G might change, the charge might change, the spin might change, but that's the rule. And you also know from classical physics, you know that if I have a, you guys know that if you have a magnetic moment, then that leads a dipole moment, then that leads to a dipole field. Now, maybe you didn't know that, because I'm not sure when you learned this, the dipole field. You certainly learn it in physics 110A, but I don't know if you learn about the dipole field in lower division physics. Do you? Does anybody remember?
I don't think so. We talked about dipoles a little bit, but I don't think we ever did field stuff with it.
Yeah, because it's kind of complicated. You know, the dipole field is sort of to actually derive it is, it's not totally trivial. Look at this thing I'm drawing. It's a vector field, okay? It's the B field of a magnetic dipole. It's a complicated object. Mathematically, it's somewhat complicated. I mean, you guys have all seen it a million times. The Earth has a dipole field, you know, magnets have a dipole field. You've all seen this picture, you know, where you get these lines of field, where that's the B field spraying out in this weird way, but you might not have ever seen the formula for it. You know, there's a kind of a complicated formula. In fact, let's write it down. We'll write down that formula right now. But before we write down that formula, I just want you to see that this is a generic formula for any magnetic dipole. You have this this magnetic field associated with it. So that means that the proton is a charged particle with spin. It has so the proton has a magnetic dipole, and that magnetic dipole is going to be G of the proton times Q of the proton. And what's the Q of the proton? Someone tell me. What's Q of the proton? Yeah, say it again.
E.
Good. Exactly. Where E we'll have E as a positive number. Okay, positive E, where that's the positive charge of the electron. That's right. And 2 over m. But now it's the mass of the proton, m sub p, in the denominator, times the spin of the proton. So that's the magnetic dipole of the proton, according to the rules of quantum mechanics. And this really comes from the Dirac equation, this rule. I did not really derive this rule, but it comes from the Dirac equation. So that's the magnetic dipole of the proton. And so that means that it has this magnetic field that sprays out. And that magnetic field, and so then what we have is the electron is in that magnetic field. And so the electron feels that magnetic field. And so that means that the electron feels it, because we know that the electron also has a magnetic dipole, and that the electron magnetic dipole is going to be G times negative E over 2 divided by the mass of the electron times the spin of the electron, which, and for the electron, we have G is 2, so we have negative E over M sub E S sub E. And so that means then that there's an energy of interaction. I'll call it H prime, the perturbation. And this is the hyperfine perturbation. And that's going to be, well, if this is the B field due to the proton, called B sub P, is this thing, what is the energy of interaction? Somebody tell me. I'll just be drawing these arrows and fixing my picture. Tell me, what's the energy of interaction?
Is it negative mu sub E dot B sub P?
Which mu is this?
Mu sub E, right?
Yes, exactly. That's right. That's it. Perfect. That's the energy of interaction, because the electron is moving around. You think of the electron as like it's in that cloud, it's in its orbital, whatever orbital it is living in, and that electron in that orbital has a spin, and that spin samples the magnetic field of the proton, because the proton is fixed. It's not moving. Proton is fixed in our approximation. We always fix the proton because it has such a high mass. And so then there's an energy of interaction. And so this is the energy of the spin of the electron as it feels the magnetic field from the proton. So it's actually quite simple. So classically, the idea is, it's very simple. This is dipole-dipole interaction. So, okay, but now let's calculate it. Now it becomes, so this is the perturbation. And so now what we want to do is let's ask ourselves, how does that change the energy level of the hydrogen atom? Okay, how does this affect the energy levels of the hydrogen atom? This is always our question. That's what we always want to know. And so let's figure that out. And so the first thing we got to do is let's figure out what that B field is due to the proton. And first I will ask you, so we see that it comes from this, the magnetic moment of the proton. Does anybody know what the G factor for a proton is? For an electron, it's 2. For a proton, what is it? This is the fudge factor that comes from the Dirac equation. Does anybody know for a proton? Okay, well, I'll tell you. It's 5.6. I thought that would be, isn't that obvious? Can't you just tell by looking at it? It should be 5.6. And here's another question. What's the mass of a proton? I'll ask it like this. What's the mass of a proton divided by the mass of the electron? This is one that actually some of you should remember. This is sort of like a famous little number. Anybody remember?
Isn't it like 1,000?
Yeah, exactly. I think it's 2,000. That's what I remember. So let's write down 2,000. I'm pretty sure it's 2,000, but that's right. It's like on the order of 1,000. And let me just ask you another question. So who has a bigger magnetic moment, the electron or the proton?
The electron.
By how much bigger?
700 times-ish, 500, somewhere in there.
Exactly. It's like 1,000 times bigger. That's right. And that's why NMR is kind of hard. That's why nuclear magnetic resonance is harder than electron paramagnetic resonance. If you want to look at the resonance signal of the nuclei, the signal is much smaller. The magnetic signal of the nuclei is smaller by 1,000 because of the mass of the proton. So that's an interesting little factoid. So that's why the nuclear magnetic field is very small, whereas the electronic magnetic field is very big. So when you take your magnet and you stick it on your refrigerator, what's causing it to stick? Is it the nuclear spins or the electron spins? I'll ask you, which do you think it is?
Electrons?
That's right. And that's why, you know, for all like magnetic stuff, for normal magnetism stuff, we're always talking about the electron spin, because the magnetic effects of electrons is way bigger than the magnetic effects of the nuclei. But the magnetic effects of the nuclei are still there. I mean, NMR comes from, you know, the magnetic nuclei, you know, spinning. So there are effects due to the nuclear magnetism, but it's much smaller than the electron. The electron one is always much bigger. Okay, so let's write down the formula for that magnetic field that comes from the proton, and it looks like this. And so this is the formula. This is the classical formula for the classical formula for the magnetic field coming from a dipole, a point dipole. And it's actually not an obvious formula. And to be honest, I actually have taught 110A, and I don't think we derived this formula in 110A. I think this is a formula that you derive in graduate school. I know it's in Jackson's book on E&M. So this is actually kind of a hard little formula, but let's write it out. Here it is. U naught times G E squared over M sub P. Oh wait, god damn it. No, I'm writing the wrong formula. Sorry. Let's start again. Wrong formula. Mu naught over 4 pi r squared times 3 mu sub p dot r r hat minus mu sub p plus 2/3 mu naught mu p delta of r, where mu naught is the nuclear magneton, E h bar over 2m sub p. We call that the nuclear magneton. Okay, so that's the formula. And so this is a famous formula from classical physics. And this is the formula. So when you draw this picture, you know, these field lines, I'm drawing an arrow at them. When you draw those field lines that do like this, then this is the formula for it, okay? And so that's why, yeah, you probably didn't, you know, see this formula, at least not in your lower division class, but you might have seen it in your upper division E&M, depending on who taught the course. Okay, so that's the formula for it. And I'm not going to derive it, but that's it. And I just want to point out that this little delta function is really important here. That delta function denotes the interior. See this arrow right here in the center? I'm sort of, you know, strengthening it with, you know, drawing on it. That little field in the center, that's from that delta function, because, you know, I got that little field in the center, and that's going to be important for today's lecture. Okay, and so now let's write down the so using that formula, we can write down the perturbation felt by the spin of the electron is going to be negative mu e dot b from the proton. And so let's dot them. So now I'm going to write the big formula. I'm going to dot those two factors, and I get this formula. This is a very famous formula in quantum mechanics. Mu naught g e squared over mp me times 1 over 8 pi 3 sp. It's quite a pain in the ass to draw. r hat s of the electron dot r hat minus s of the electron dot s of the proton. Okay, divided by r cubed plus 1/3 times se dot sp delta of r. Now it doesn't matter what order I do the mu and the b, because I'll ask you, does the spin, if I take the spin operator for the proton and the spin operator for the electron, do they commute? Yes or no?
Yes.
That's right. Good. They do commute because they act on different things. All right. Like momentum and position and momentum for an electron do not commute because they both are acting on the electron spatial wave function. But the spin of an electron operator and the spin of the nucleus operator, they're acting on different things. One is acting on the electron wave function, one is acting on the nuclear, and so they commute. I just want it to be clear. Okay, so this is this is the perturbation, and so now let's ask a question. So it's kind of a complicated perturbation, it's a big ugly formula, but it's not hard. It's just mu dot b, so it's just, so once you know that classical B field, it's easy to derive this once you know that starting formula. But now let's ask ourselves let's ask a very specific question. How does this split the ground state energy of hydrogen? How does this split the ground state energy of hydrogen? Now, whenever somebody says split, then they're immediately implying that the level that's being split is degenerate. And so I will ask you, what is the degeneracy of the ground state of hydrogen? Ah, shit. Sorry. I'm always putting this thing into weird modes. How can I get out of this mode? Can you guys see the screen? Do you see it? Yeah? Okay. So, all right. So what is the degeneracy of the ground state, of hydrogen?
The 2?
Well, that's a good guess. And that would make sense because spin is up or down, and that's 2. That's good. But it's not quite right. What are we missing?
Are we missing the proton spin?
And what's the degeneracy of the how many proton spin states are there?
2.
Okay, so what's the total degeneracy of hydrogen?
4.
Right. Because if we include the proton spin, there's 4. So the degeneracy is 4. And so that's what we're talking about. So when we're talking about the ground state energy, it's a whole new ballgame because we want to use perturbation theory, but now our wave functions are many-body wave function. The wave function is going to be the wave function of the electron times the wave function of the proton. You see, it's a many-body wave function, MB, many-body, because we have 2 particles, the proton and the electron, and they're both quantum because the proton has quantum spin and the electron has quantum spin. They're both quantum. And the electron wave function, well, what does that look like? What does the wave function of the electron look like in the ground state? Somebody tell me. ground state energy of the hydrogen atom. What is the ground state wave function of the hydrogen atom? That's what I'm asking.
Like an EV?
I'm asking for the wave function.
Oh,
The asymmetric one, right?
Are you talking about symmetry? Like you mean like symmetrizing the many-body wave function? Is that what you mean?
Yeah.
Okay. Well, here I have two particles, one electron and one proton. So I'm glad you raised that issue. Do I have to symmetrize the wave function? Somebody answer the question.
No,
Why
because
not?
they're not identical.
Exactly. Haha, they're not identical. So all that symmetrization stuff that we spent so long on before, we can just throw it out the window. Don't have to worry about symmetrization. But I'm glad you brought it up. But now I'm asking, what is the wave function, the ground state wave function of an electron in a hydrogen atom? Just the one electron. Forget about the proton.
It has the radial and the angular part.
Yeah, good. It has a rate. That's exactly right. So we'll write it like this. So N L M sub L, right? But then it also has the but we also have the spin, right? We have the let me just make sure I'm using the right notation. Then we also have the so that's right. So that's the spatial part, but we also have the spin part, right? And so now I'm going to write the spin. I'm going to write it out in a little bit more detail because we have to keep track of the spin of the proton, the spin of the electron. So we have the S sub E, the spin of the electron, and the M sub S sub E, the M sub S for the electron. Okay, so that's the wave function of the electron. And now I'll ask you, what's the wave function of the proton? Somebody tell me. Well, here I'll ask you a first question. Do we have to worry about the spatial part of the wave function of the proton? Yes or no?
no, since it's in the middle and it doesn't move.
Exactly. So we don't have to worry about that. So the wave function of the proton is only the spin part. But what is the wave function? What is the spin part of the wave function of the proton? Tell me.
Isn't it the same as the electron, just with a P instead of an E?
That's exactly right. That's exactly right. It's a spin 1/2 object. So basically its wave function is just up or down. And so this is just a fancy way of saying up or down. Okay, so that's it. And so that means then that my wave function, my ground state wave function of my hydrogen then is going to be, well, for the ground state, N, for the ground state, what does N equal? N equals what? For the ground state, N equals what?
It's 1.
Good. And if N equals 1, then L equals what?
0, and M is also 0.
Perfect. So that means my wave function for my ground state is going to be psi 1, 0, 0. And that's a function. That's my ground state wave function. And you can look it up in a book. And then I'm going to have my spin part. And then I'm going to have my my proton part. My electron part spin and my proton spin part. Okay, so maybe I'll stop. Maybe I'm going to change this notation. Instead of saying M sub SE, I'm just going to say M sub E. Let's see, is that how I did it? That's why I keep my notes consistent. Oh, it's a terrible, terrible notation that I was using. because it gets you confused with the mass. I think I'll stick with the m sub se. Okay, that's the wave function of the ground state of hydrogen. And you can see how it has a degeneracy of 4 because, you know, I can have, you know, up, 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 down, 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 up. Okay, so there's 4, you know, 4 states here. And so now I want to find the change in energy due to the hyperfine. And so what do I do? Somebody tell me. Well, I'll tell you what I want to do. I just want to plug it into the formula for perturbation. I just want to do the expectation value trick, right? I just want to do this trick. I just want to say, you know, that the energy correction is equal to the state sandwiching the expectation value of the perturbation. You know, that's our favorite formula. That's what I want to do. But before I do that simple formula, I have to go through a litany of tests. So what's the first question I ask? What's the first question I ask? I want to, yes?
If that one component 0 or not, that psi n psi m one.
Yeah, that's right. Exactly. Good. So first we ask, is it degenerate? But we already said that it was, so we know it's degenerate. And so second, I have to know, are the off diagonal matrix elements equal to 0 or not? For I not equal to j. So we have to check that. But let's do the trick. Let's do our elegant trick, because we know that our basis states are now psi n. Well, actually, I'm sorry. I don't need to write all that. It's 1, 0, 0, m sub e, m sub p. Oh, now I'm doing I'm changing my notation midway. I guess I shouldn't do that. Okay, it's m sub s e, m sub s p. Okay, that's our basis, where this quantum number comes from the operator s z for the electron, and this one comes from the operator s z for the proton. And so we have to ask ourselves, is it a good basis? Is this a good basis? And so to see if it's a good basis, we're going to use our trick, use the math trick. And so we're going to look at the commutator of the perturbation with some operators. And we're going to ask, is that equal to 0 or not? Now my question is, what operator goes there? Somebody tell me.
S sub z for both the electron and for the proton.
That's exactly right. S sub z e. And we also have to check if h prime s sub z p equals 0. That's exactly right, because those are the operators that index the degenerate subspace. So I just want you to see how it's the exact same trick that we used before. It's always the same, even though the details might change. So let's answer that question. And so let's answer that question. So H prime is this big ugly formula. I wrote it up here. There it is. Okay, big ugly formula. Here it is. I'll put, see, 2 little stars, 3 little stars on the right. See them? That's the formula. But we don't need to worry about all that formula. All we got to worry about, let's just look at this last part of the formula right here. Okay, because that last part of the formula has SE dot SP. And so let's just plug that into the commutator because that's part of the perturbation. And now I'm asking you, does the H prime commute with SZ and SZ for electron and SZ for proton? Does it?
Professor, could you explain again why we're using SE.SP?
Sure. The simple answer to your question is because it appears in this big formula in the middle of the page, on the right-hand side of the formula. Is that sufficient to answer your question, or do you want me to go into more detail?
So I see that it's like directly the right hand term, essentially. But then how do we know that that would guarantee that H prime itself actually commutes with the operators?
Well, what's going to happen is we're going to find that it does not commute with that.
Oh, okay, I see.
And so to do it correctly, we would need to find the commutator with this whole ugly formula. But that's too much work.
Okay, gotcha. Thank you.
I'm too lazy. I don't want to do it. So let's just do shorthand. So the shorthand, because this is like the way to do it correctly, you got to find the commutator of the S sub ZE and the S sub ZP with this whole gigantic ugly thing. But what I'm telling you is that a shorthand trick is to just pick that one part, because now when you look at it, it should look familiar to you. What does it remind you of? What does it remind you of? It should remind you of something that you've already studied and you've already worked out in great detail.
The orbital angular momentum.
Say it again, please.
The orbital angular momentum operators.
Yeah, that's right. But this formula, SE.SP, reminds you of what other formula? Can you tell me another formula that looks like that we studied before?
L.S.
Yes. It's like L.S. From a mathematical perspective, it is identical in some mathematical sense to L.S. because L.S, L is an operator that represents angular momentum. S is an operator that represents angular momentum. So L.S is the dot product of two operators that represent angular momentum. Now notice S sub E is the spin of an electron. That is also an operator that represents angular momentum. S sub P, the spin of the proton, is also an operator that represents angular momentum. So S sub E dot S sub P is the dot product of two operators that both represent angular momentum. So from a mathematical sense, this new perturbation is identical to the spin orbit. At least this part of the perturbation that I've written down. S sub E dot S sub P is identical to L dot S from a mathematical perspective. Okay, well, using that kind of reasoning, we now have, so remember when we did this? Remember this, L dot S, S sub Z. Was that equal to 0? Yes or no? Well, to speed things along, I'll give you the answer, because I know it's hard for you. Can't remember all these commutators. I mean, I realize, nobody can remember everything. So it doesn't equal 0. This is what we determined. Remember when our old basis, the psi, n, l, m sub s, the old basis was a bad basis, and we had to go into the J basis. And the reason why we could see that the old basis was a bad basis is because L dot S does not commute with S sub Z. And that's why the old basis was a bad basis for spin orbit. I'm just reminding you, we went through that whole argument. And so now, if you know that L dot S, comma, S sub Z commutator does not equal 0, then now I'm asking you, how about this commutator, S sub E dot S sub P, comma, S sub P Z. Oops, I wrote it the wrong way. So if this does not equal 0, what can I say about this? Does it equal 0?
No.
Exactly, it does not. If you go through the commutator logic, the commutator algebra, you will work out, and I think it's part of your homework. I hope it is. You should work it out. You can see that it does not equal 0 by the same reasoning. What I'm trying to do is I want to show you that the reasoning is identical to spin orbit. So the whole logic and mathematical formalism of hyperfine is identical to the mathematics and logic of spin orbit. It's the same problem, just with different notation. So I'm trying to make you see, I'm trying to get you to see that. Okay, good. And so that means if this commutator, that means that these commutators do not equal 0. They do not equal 0. And so that means that, what can I say about this basis then? So what does that tell me about this basis? Psi 1, 0, 0, m sub s e, m sub, this is my basis. Is this a good basis or a bad basis?
Bad.
Good. Sometimes bad is good. Exactly. Bad. That's a bad basis. Okay, so now we have to find a good basis. So what are we going to do? We got to go to a new basis. What do you think that new basis is? Let me sort of help you along here. So this basis is indexed by the eigenvalues of S sub z for the electron and S sub z for the proton. So now I want to find a new basis, and I'm going to help you along. It'll be psi 1, 0, 0. But now I'm going to replace these two quantum numbers with two different quantum numbers. What will they be?
The combined angular momentum.
Exactly. That's exactly right. S total. Let's write it like this. S total. And what goes here? What's the next one? What's the next one?
The z component?
Exactly. M sub s total, where this is the eigenvalue of the operator S total is equal to SE plus SP. And this is the eigenvalue of the operator SZ total equals SZE plus SZP. And this is exactly what we did for spin orbit. So I just want you to see it's exactly the same thing. This was for spin orbit, it was the J basis. It was J for spin orbit. It was J. Remember, for spin orbit, we then went to the J basis, which was J equals L plus S. And then we had the J states J, MJ. Okay, where this was, and this ST is actually the eigenstate of, it's actually the eigenstate of not ST, but I should say ST squared, right? Because J is the operator of J squared, and M sub J is the operator, is the eigenvalue of JZ. So here I'm replacing, so here basically we're replacing J with S sub T and M sub J with M sub S sub T. Okay, so we're going into the total angular momentum basis. So the good bit, and so let's try this basis, psi 1, 0, 0, S total M sub S total, where this is the eigenvalue of S total squared, and this is the eigenvalue of S total Z. And so now we have to ask ourselves, is this a good basis? We have to check. Is it a good basis? This is a new basis that you just made up. And is it a good basis? Well, to check, we have to do a commutator of H prime with what? What goes here?
ST squared and STZ.
Exactly. And H prime, just the only part that really matters is this part, S sub E dot S sub P, the spin of the electron and the spin of the proton. And when you do it, you'll find that indeed it does equal to 0, just like spin orbit. So I'm not going to go through that algebra, but I think you can trust me on that one because it's exactly the same as spin orbit. So that means that this is a good basis. And so that means that now we can use our little formula, because that means now that we can use our formula, but because if so long as we use the good basis, then our little formula works. So now we can say delta E is equal to psi 1, 0, 0 S total M sub S total H prime psi 1, 0, 0 S total M sub S total. Okay, and we just have to calculate this. And so let's calculate that. And it's, you know, slightly painful to calculate, but let's just do it. So what we can do is we have that big formula. So I'm going to do it like this. I'm going to write this state like this. I'm going to write this as psi 1, 0, 0, the spatial part, and then I'm going to pull off the spin part, S total M sub S. Actually, I'm going to use this notation. I'm going to call this M total. Okay, that's the notation I'm going to use. And so using that notation, if I plug in the H prime, and I'm not going to, here's the H prime from before. It's this big ugly sucker up here. Here it is. And so let's plug it in there. And so when we plug it in, we're going to see that all we got to do is just, now we have our good basis and we have our Hamiltonian. We just plug it in. That's a bunch of algebra, but I can write it all out. And if I write it all out, then I can see that it's equal to this. And you guys can do this just as easily as me. There's no tricks. It's just a bunch of work. I mean, it's just a bunch of algebra. M sub P, M sub E. Then I have a 1 over 8 pi. Then I have a psi 1, 0, 0. S total, M total. Then I have my my 3 times SP dot R hat, and I have my SE dot R hat minus SE dot SP divided by R cubed, sandwiched into the spin and spatial wave functions, and then I have to add plus 1/3 psi 1, 0, 0 S total, M total, SP dot SE delta of R ST MT psi 1, 0. Okay, so that's what you get when you sandwich it in. And so it's not hard what I did, but I just, I just skipped a little algebra. And now here's a trick. It turns out that you see that there's 2 terms here. You got, I'll call this term 1, and I'll call this bottom part term 2. You see how there's 2 parts to this. I just broke that, and it comes from this big ugly formula, right? See, this big ugly formula has two parts in the middle of the page. And so that's where these two parts come from. And so here's the trick. The trick is to notice that part number 1 is equal to 0. And that's not totally obvious from just looking at it, but it's problem, you can calculate it from problem 7.31 in Griffith's. Third edition. And the justification for it is, so go to that problem and you can see that it's equal to 0. And the physical justification is this, is that if you have a dipole, you know, it goes like this, right? And this part, you see how in this region, well, I'll just ask you, in this region, the field is pointing in what direction? Up or down? The B field. Which way is it pointing, up or down? In that region that I circled. Say it.
Oh, up.
That's right. And in this region, which way is it pointing?
Down.
Yes. And so if I just look at the field, you can see that in one region it's up and the other region is down. And so that means that when I integrate over space, which is what you do in that matrix element, term 1, they cancel, okay? You get cancellation. But at the center, I only have up at the center. And so this second term represents the center part and it does not equal 0. So that means that delta E is equal to the second term, okay? So I have to calculate the second term, and to calculate the second term, what we have is, it's gonna be mu naught G E squared over 3 MP E. And now I'm gonna pull the spatial part over, and it's gonna have psi 1, 0, 0 delta of R, psi 1, 0, 0, and then the spin part is gonna be here, S total, M total, S dot P, SP dot SE. And so now we have to calculate this. And this turns out to be pretty easy because these two parts are easy, because this part is just going to be the integral of psi star 1, 0, 0 delta of R psi 1, 0, 0 E cubed R, which is just going to be equal to psi 1, 0, 0 evaluated at R equals 0 squared, right? I would call it psi 1, 0, 0 of 0 amplitude squared, because that's what the delta function does. It just picks the center point. So that's just the wave function evaluated at the origin, and it turns out it's not divergent. It has a nice, well-defined number there. In fact, I can even write it down. Where is it? It's equal to 1 over pi a naught cubed, where a naught is equal to the Bohr orbit, h bar squared over m c squared is equal to 1/2 angstrom. But then this part is a little trickier to evaluate, but now we can use the spin orbit trick. Here we use the spin orbit trick. Where we can say that S total is equal to SE plus SP. And then when we square both sides, we get S total squared is equal to SE squared plus SP squared plus 2 SE dot SP. And so SE dot SP is equal to 1/2 S total squared minus SE squared minus SP squared. So that's the trick. That's the spin orbit trick that you've seen before. And so now I'm going to plug this into there, and then we can see, then we can evaluate it, because then you can see very easily that S total, M total, SP dot SE, I'm just going to replace it with this new thing, which is 1/2 S total squared minus SE squared minus SP squared, acting on ST MT. And so when S total hits it, what is this equal to? What is that going to turn into? Can you tell me? Well, we're running out of time, so maybe I'll write it down. It's just H bar squared S total times S total plus 1, and SE squared, when it hits this guy, they're all eigenstates, then it's H bar squared SE times SE plus 1, and this guy is going to be H bar squared SP times SP plus 1. And so when I plug that in to this formula up here, I'm going to get that the energy correction due to this hyperfine, when I plug all those numbers in, it's just going to be this. It'll be U naught GE squared over 3 MP ME times 1 over pi K naught cubed times 1/2 H bar squared times S total plus 1 minus 3/2. That's the answer. And so what we can do then is we see that we get a splitting. We see that it splits S total. And so for hydrogen, the ground state of hydrogen is going to be these four states, the degenerate 4 states. But now the degenerate 4 states are going to be, I had the electron has spin 1/2, the proton has spin 1/2, and so that means that I'm going to have a singlet, S total equals 0, and 3 triplets, S total equals 1. And this is M total equals 0, and M total equals 1, 0, and 1. So those 4 states, which were, up, down, up, down, down, up, down, down, up, now we write them as a singlet and 3 triplets. But now they're in the basis of the spin and electron. We're adding the spin of the electron and the proton. And so we see that this is going to now split into 2 levels from this formula. And we're going to get some change in energy between them, delta E. And so if you calculate this delta E from this formula, where this is the higher state is S total equals 1, and the lower state is S total equals 0, then you get some energy. And if you plug in all the numbers for hydrogen, you just plug them all into that little formula, you get a number. And if you divide that energy by H, Planck's constant, you get a frequency. Does anybody know what the frequency is? Just thought I'd ask. It's 1420 megahertz, which corresponds to a wavelength of the electromagnetic radiation. Does anybody know what that wavelength is?
I think it's 21 centimeters.
That's right. So this is the famous 21 centimeter line from astronomy. And so this is how astronomers see dust clouds. Astronomers use this to see dust clouds, because what astronomers do is they look for this. Astronomers see hydrogen dust in the dust clouds of the universe, and they find this to be very useful. because the idea is that the hydrogen is bouncing around in those dust clouds, and the hydrogen every now and then is getting, just from some random interaction, is getting kicked up and then falls back down from this one quantum state to another. And these dust clouds are radiating 1420. They're all just radiating 1420 out in the universe, and the astronomers can see it. Okay, folks, sorry for going over. That's it. Talk to you later. Bye-bye.
Thank you, Professor.